Stoichiometry. When we talk about stoichiometry, it's bringing everything together that we've been doing this year. So like writing equations, balancing equations, writing chemical formulas, balancing chemical formulas, knowing the charges on everything. It's everything coming together. Plus the test that you just took, that was yesterday, right?
Yeah.
So the moles, we're still going to do that.
Yeah.
So it's bringing everything that we've done so far this year into one topic, which is known as stoichiometry. Stoichiometry rocks. Now, when we talk about stoichiometry, we're talking about a quantitative description of proportions of moles. So when we look at the periodic table, and you have your periodic table out, like a good chemistry student would. And actually, let me get mine out. I'm working on it. Okay, so just as a reminder, the reason why we worked with moles last time and why we're going to continue working with moles is because not all the elements have the same mass per mole. So even though like chromium's 52 grams per mole and say gold is like 196.97 grams, if we say that we're looking at the same number of moles, we're looking at the same number of particles. So that's what stoichiometry does. It allows us to change the masses into moles, and then we can use a proportion based on that. So it'll make more sense once we start doing some examples. So go ahead and get the blanks here, and then we'll dance right into it.
Yes.
Oh yeah.
Yes.
Okay. And I hate to say it, but really, most of the things, if I were to read these statements to you, would be just what we've been talking about all year so far. Okay. So balancing the equations, balancing the charges, writing out the chemical formulas correctly, pretty important stuff. I've heard some people, you won't hear me refer to it, but some people call this the bookkeeping of chemistry when we talk about stoichiometry. If you want to do that, that's fine. If it makes you happy, I guess. Let's see, what else? All right, also, when we work with stoichiometry, we're generally going to be working with what's called the theoretical maximum. In other words, like in the lab that you just turned in with the hydrate, none of you got the actual value for what the water should have been. Because again, we didn't break up the water molecules down. For the lab equipment that we have, it's very difficult to get all the water evaporated out without decomposing it. So we talk about theoretical maximums. So when you hear about a theoretical maximum, you're talking about a utopian type situation where it's perfect, where everything is going to work exactly as our calculations say.
Utopian.
You've got something to learn there. That's good.
That's awesome.
Okay. When we talk about chemical formulas, like the coefficients in front of these elements, or I'm sorry, these compounds and elements, these represent a ratio for our balanced equation. Now, this would be the more optimum equation to have, because again, these are not our smallest whole number ratios. So we still want to make sure that, yes, even though we're looking at this equation and that equation, proportionally, they have the same ratio. But we always want to go with the smallest whole number. Again, reactants are the things that you start with. Products are the things that we finish with. So when we look at the balanced equation, we're talking about the ratio of the reactants to the products. And there's an example problem I'll let you look over on your own leisurely time. Okay, let's get all the blanks first before we start doing. So the homework, the ones are part of your homework. If you have a highlighter, get your highlighter out, because you need to highlight these 4 steps, which is on page 5. So again, highlight these 4 steps. They're right in front of you. It's in big. Now, the nice thing about stoichiometry, every single problem, you'll go through these 4 steps. Every single one of them.
Every single one?
Every one of them. Now, what's nice is sometimes the step will already be done for you or completed for you. But we always want to go through these 4 steps in every problem. First one, always write a balanced equation. So we're going to start off with our reactants and our products, and then we'll balance out the number of atoms on both sides. Number 2, it says write what you know and then change that starting quantity to moles. So sometimes it'll be in moles, like our first set of examples.
Grams.
And sometimes it'll be in grams.
Or atoms.
Sometimes well, we're not going to go that way. But molarity is another one. So there's all different ways that you can actually have it, but you want to convert it to moles. And you have the skills to do that. Number 3, we're going to use what's called a mole ratio, and that'll make more sense once we actually do the problem. And then the last step is convert the new moles into the requested units. So you will change what you started with into something different, and then we'll go to the desired units. Okay, and we'll do some more examples here. Okay, so there's examples 3 and 4, and the 2s. Okay, mass to mass. I can't remember how many different blanks we have on this one.
A lot.
There's 1.
There's just one.
Is there just 1?
Yeah, there's one.
Yeah.
Awesome.
But you can try all along.
All right, so let's do some examples. Example number 1, it reads, ammonia, which is NH3, is synthesized from hydrogen gas and nitrogen gas. If 3.8 moles of nitrogen gas reacts with hydrogen gas, how many moles of ammonia would be produced? Now, you're going to find out that most of the stoichiometry type questions are just like this. There's a lot of information. You have to be able to decipher the information and interpret what's going on. So starting off with ammonia is synthesized. What does that mean? Is it produced or something you start with? NH3 is ammonia. Synthesized from hydrogen gas and nitrogen gas. So how do you write it?
N2.
So H2 and N2.
Why would it have to be 2 of them?
Because of gas.
Because it ends in GN.
Ends in gen.
So gas.
Well, not necessarily because it's a gas. Anything can be a solid, liquid, or gas. Just depends on the temperature. Okay. Also, what I highly recommend is write down the information that's given. So it says 3.8 moles of nitrogen. So this is information that's given to you. And what's the question asking?
How many moles of ammonia would be produced?
Good. So how many moles? So once you have that, theoretically, you don't need to see the question anymore.
No.
Okay? So once you've written down the balanced equation and you write down what you know or what you're looking for, there's no reason to go back to the question. So step 1, write a balanced equation. Is that balanced as written?
Probably.
It's not. Sometimes it will be, but in this case it's not. We have 2 hydrogens here and 3 there, so that right there tells us it's not. So we'll put a 2 there. How's our nitrogen looking?
Radical.
And with 3 there. Okay? So we have step 1 completed. Step 1 done. Okay? All right, step 2 is to take what's given. What's given here?
3.8 moles.
Yeah, not the number of moles of the ammonia. That's what we're looking for. So we're going to start with what we know, which in this case is 3.8 moles of what?
Nitrogen.
Nitrogen. And I want to know how many moles of ammonia are produced. So I've already got it in moles, so step 2's already been completed for you.
Calculate like NH3.
Wait, what?
Okay? So step 2 is finished. It's already been done for you. It's already in moles. Step 3 is I need to get rid of the unit moles of nitrogen because what am I looking for?
That one.
The moles of ammonia. So I'm going to put moles of ammonia up here. Now, how did I know to put nitrogen on the bottom?
Because that's where it cancels out.
So I can cancel it. Very good. So if I were to do some canceling, then the moles of nitrogen go away. But I need to put some values here. The whole reason why we write a balanced equation is for step 3, so that we can have the proper mole ratio here. Which, if I look at the balanced equation, what coefficient do I have in front of the ammonia? 2. So I'm going to have a 2 there. What coefficient do I have in front of the nitrogen? 1. So what this is saying is, even though I have the 3 moles of hydrogen, I have 1 nitrogen. So for every 1 mole of nitrogen, I'm going to produce 2 moles of ammonia with the hydrogen. Okay, so that's why we balance the equation first for step 3. So if I were to stop right here, I would have what unit?
Moles of ammonia.
Of ammonia. Isn't that what we're looking for?
Probably.
Oh yeah. Okay, so step 4 was already completed for you because it was already in the unit moles.
7.6.
Just 7.6. I like that. Okay. Wasn't that fun?
No.
Is that all?
It's gonna get way
That was it.
more
Yeah.
That's easy.
Yeah, it is easy.
Yeah, that's the first one. Wait till.
All right. Well, let's do number 2.
You always do that.
Oh, come on now. I'm not going to throw the hardest question at you first. All
I would like that better. I would like that better.
right. Number 2. Glucose, C6H12O6, decomposes into its elemental components, carbon, hydrogen gas, and oxygen gas. In a decomposition reaction, calculate the number of moles of glucose needed to form 22.4 moles of hydrogen gas. So what's the first thing that we're going to do?
It's
Balance the equation.
Okay, who are my reactants?
Carbon.
This?
yeah.
Since it says it decomposes, so C6H12O6, and it decomposes into what?
Carbon, hydrogen, oxygen.
Carbon, hydrogen, and oxygen. Okay.
Right, H2.
All right, so there are my things that it decomposes into, boys.
Balance it out.
And, no, not yet. Let's write down what we know. So what do we know about this?
22.4 hydrogen.
We have 22.4 moles of hydrogen. And what's the question asking?
Numbers of moles.
Calculate the number of moles of glucose.
Okay. Now, some of you may have looked at the last question and said, oh, he gave us the information of the reactant. We were looking for the product. This time he's giving us the product and we're looking for the reactant. Can go either way. All right, so don't freak out. It's still good. All right, so we know the hydrogen. We know we're looking for the glucose. We don't know anything about the carbon or oxygen. Don't worry about it. It's all right. So step 1 is to
Balance.
write a balanced equation. Is that balanced?
Nope.
No.
6 on all of them.
6 on the carbon?
Yeah.
663.
663, yeah, what you said.
3. Good. Okay. And the 1 here?
No.
Nah.
Yeah, it's good.
No.
Yeah, so it stays as 1. What do we know?
Now we find moles.
We gotta put the moles on the bottom, or on the top.
We're going to start with what we know. We know we have 22.4 moles of
Hydrogen gas.
hydrogen. Okay? So step 2 is to change what's given in the moles.
That's already
It's done. Step 2 is already finished for it. Okay? Step 3 is to change what was given, use the mole ratio. So we want to get rid of moles of hydrogen. And what are we looking for?
Moles of glucose.
Glucose. Very good. Again, the reason why we have to change it to moles is because these don't have identical molar masses. However, if I have 1 mole of each, then I have the same number of particles. And that's what we're looking for. So what values go in front of the hydrogen and glucose?
6.
So a 1 and a 6. Okay, I can go with that. And what's the question want it to be in?
Moles.
So we're done, aren't we?
Yeah, it's 3.73.
That wasn't hard.
It was.
Isn't that easy?
Yeah, it's easy.
Super easy.
Easy
It's
way.
gonna be hard.
All right, turn to example number 3,
Where's that?
On page 7.
page 7. Okay, and again, still using the same 4 steps. Example number 3. It says, a synthesis reaction is performed in the lab where 14.6 moles of potassium react with nitrogen gas to form potassium nitrate. Calculate the mass in grams of the potassium nitrate that was created in this reaction. So who are my reactants?
K and
Potassium.
N2.
Good. So it says reacts with or react with. So we're going to say that that's on the left side. And nitrogen gas is N2. And what is it for me?
Potassium.
Potassium nitrite. KN.
So Kn. Now, what's the charge on potassium?
That's it's a 1.
Plus 1. What's nitrogen?
-3.
Negative 3. So is that balanced as written?
No. So the K is 3.
So we need a 3 there, right?
Yes.
Good. All right. So make sure that you're balancing charges, if it's ionic, and that is. Let's also write down what we know. What do we know?
14.6 moles of potassium.
Okay. And what are we looking for?
The potassium nitrite in grams.
Grams. So we're looking for the mass. So we're looking for grams this time. Okay.
We balance it out.
Okay. So step one,
Balance.
balance it.
So would it be
It'd be
3?
six.
Would it be?
Put a
Yeah.
six.
Well, we have 2 nitrogens, 1, right?
So 2.
There.
2 there.
And put a 6 on the cage.
There we go. Okay.
Then we solve.
What do we start with?
14.6 moles. Of
So we start with what we know, which is 14.6 moles of potassium. So take what was given and convert it into moles.
Yes.
Done. Okay. So step 2 is finished. So again, step 1, write a balanced equation. Step 2, change what was given into moles. Step 3,
Get into the desired whatever.
well, we have the mole ratio.
That's what I meant.
So we need to get rid of moles of potassium. And what are we going to change that to?
moles
Moles
of
of
K
potassium
and 3.
nitrate.
K3N.
Okay. What numbers go in front?
2, 6.
2 there and a 6 there.
Yes. And
Now, little sidebar. That's a 2, that's a 6. Should we reduce that?
No.
Don't. Because if you change that to a 1 and a 3, you're going to come back to the balanced equation and go, where'd you get a 1 and a 3 from?
Yeah.
I'll know what it is. But say a week from now when you're going through looking at these problems and trying to just review, if you have a 1 and a 3 there, that might cause you to go crazy. So just write down what we have from the balanced equation because you have the lowest whole number ratio here. Okay? All right. Are we finished?
No.
No, we need to change. If we stopped right here, we'd have moles of potassium nitride. We need to change it to moles of, or I'm sorry, grams. Now, again, when you're looking for molar mass, it's the number of grams per 1 mole. So whatever's on your periodic table. So again, we have 3 potassiums plus nitrogen.
131.31.
131.
I believe. I think so.
131.
I think so. I just guessed.
Double check here. Not that I don't trust you. That's a good number, Tim. Okay.
Right.
All right. So right now, if we cancel out our units, we're looking good, right?
Yep.
And then whatever that equals.
And 639.042, I believe.
639.
Yeah, grams of K3N.
Yep.
I think. I guess it's
Is this difficult yet?
yeah.
Not really.
Yeah. Easy.
Easy stuff.
Methamphetamine.
Pretty easy. And again, remember the 4 steps. Step 1, write a balanced equation. Step 2, change what was given into moles. Step 3, we need to get rid of what we started with. And what we start with will always be on the bottom in the mole ratio. What we're looking for will always be on top. And then change it to the desired unit.
Methane.
Number 4. Oh, it just gets better. When 575 grams of methane, which is CH4, reacts with oxygen gas in a combustion reaction, the products of a combustion reaction are formed. You already know that. What are the products in a combustion reaction?
C. Is it CHO?
CO2 and H2O.
Yeah.
Carbon dioxide and water. Same stuff that you breathe out. So make sure that you do know that. Calculate the number of moles of water vapor. What's water vapor?
Evaporated water.
H2O. Very good. Okay. So don't freak out when I tell you it's water vapor, or vaporous water, or anything like that. Remember, anything can be a solid, liquid, or gas, including you. Just depends on how much heat is present. All right. So what do we start with?
Methane.
CH4. Good. And it is reacting with what?
Oxygen gas.
Good.
O2.
O2. And it's forming what again?
C2O, CO2, H2O.
Okay. And do we know anything?
Yes. No.
175
Yeah,
grams
grams of methane.
So we have 575 grams of methane.
Me methamphetamine.
And we're looking for
Number of the moles of water vapor. So
Moles of water. Good. So moles. So this ought to be super easy.
it's easy.
Super easy. So again, once you have that information, and again, I highly recommend that you put the information above either the element or the compound, just so you don't have to go back to the question. So are we balanced?
No.
No.
I got it. We need 2 on O2 and 2 on H2O.
2 on O2 and 2 on H2O. Does everybody agree with that?
I do.
What? No.
It's balanced. Okay? All right. So what are we going to start with?
Grams of 575 grams.
So start with what you know, which is 575 grams of methane. And we need to step 1, write a balanced equation. Step 2, change what was given into moles. So 1 mole of methane. Oh, not 16, sorry.
16 point.
I was getting ready to write oxygen. So 16 point.
042.
Okay. All right, so all of this is step 2. Okay.
Okay. Well, I have
Don't worry, it'll be.
I have a question.
We'll give you more information later. Yeah.
The second top one, what's the 1 mole CH?
Oh, I'm sorry.
Would be H2O.
It'd be CH4
Wow. Oh.
because that's what was given.
Oh yeah.
All right, so we want to get rid of the unit that we started with. So we're going to get rid of moles of CH4, and what are we looking for?
Moles of H2O.
Moles of water. Okay. And what numbers are we going to put in front of those?
2 and 1.
So again, from the balanced equation, a 2 here and a 1 there. And what's the question asking us to do? Oh, it's right there.
And the number of moles.
Moles of water. Where are we at if we stop right there?
And it's
Moles of water. Now, this is one reason when you're doing your mole ratio, I highly recommend that you not only write mole, but also what it is. So that you're sitting here, you're not like, well, what's that moles of? Well, in the mole ratio, you want to write what it is so you know that you're actually putting the correct value in. Because if you just put mole on there, if you just did this,
will that be right?
good luck. No, it won't be right because you don't know what that is. So you definitely want to have what it is.
And it's
Okay.
71.7 moles.
It's what?
71.7. Yeah. That's-
Now, at the end, you don't have to put H2O on there unless you just
If
dyed.
you do, is that wrong?
It is not. Unless you wrote methane. Okay. Yeah.
Where do we find the number before the mole?
Where do we find this value?
Yeah.
From your balanced equation. So step 3 and step 1 are like cousins.
Are we done?
No, we have 2 more. 2 more, buddy. Here we go. Number 5. Oh, this is a good one. Oh, this is the big one. All right, number 5. What page is that on? Okay. One way to remove carbon dioxide from the air that must be recirculated, such as in a spacecraft capsule, is to react it with lithium hydroxide to form lithium carbonate and water. How many grams of lithium hydroxide are needed for a 6-day, 3-person mission if in 1 day each person exhales 1 kilogram of carbon dioxide?
No.
Man, oh man. That is a lot of fun stuff there.
So CO2 produces lithium thingy.
Okay, well, hold on there. So we know we have carbon dioxide. That's our main thing that we need to be focusing on since we're trying to get rid of that. And we're going to react it with what?
Yeah.
Lithium
Lithium hydroxide.
Yeah. LiOH.
And what are the products here?
Li2CO3.
Lithium carbonate. And what else?
And water.
And water. Okay.
H2O.
All right. Now, what do we know? Actually, what are we looking for? Let's start there.
How many grams of lithium OH?
Good. So we need to know how many grams of this. Okay. What do we know?
We need 6 days.
One.
So we know we have a 6-day mission person,
3 people, not person.
3 person per day. They're exhaling how much?
1.0
1 kilogram per person.
Carbon back.
Okay. So how many kilograms of carbon dioxide should we be
18.
concerned about?
18.
Yeah, so that's probably a good thing to know. In other words, what we don't want to do is like say, oh, it's only for 3 days, okay, and then have your crew dead on the halfway point, or not take into consideration everybody that's in the cabin and breathing. So in this case, we have 18 kilograms. Okay. So balanced, is it?
No.
What should I do? Put a 2 here?
No.
Yeah.
How are we looking now?
3 on CO2.
I like what we got.
Should I?
No. But the OH.
I thought the oxygen. No, never mind.
Oh, no, that's
I
wrong.
like it too.
It's CO3. Oh. Oh.
What's the matter, Timmy? You all right?
I can't see that far.
Okay.
Can you explain?
Yeah, it's balanced. Very good. What do we know? Let's start with what we know. 18 kilograms, good.
Yeah.
And we need to change that into
Grams.
good. When eventually we'll get it to moles. So which is bigger, kilogram or gram?
Grams.
Gram. So there's 1,000 grams in a kilogram, and on the test, not in this class because I haven't graded this one yet, but in the other classes they were saying, a couple of the students were saying there were 1,000 kilograms in a gram. Come on,
Kids these days,
what
right?
rookies. Okay, so we need to find out how many moles of carbon dioxide. So what's the molar mass for that?
That. Gosh, I'm so behind.
I know, Tim, it's all right.
No.
So 44.01, is that what I heard?
Yeah.
Okay, so all of this is step 2. Remember way back here where it was given to you?
Yeah, that was nice.
That was fun. Those were the good old days. Now, we're here.
Oh, grams of what?
Grams of what? What do you mean?
Like what? Like CO2 or what?
What are we talking about? Here?
No, the grams down there. The
Here?
grams.
This is for our carbon dioxide. Is that what
Okay.
you're saying?
Yeah.
Timmy. All right, so step 3 is to do what?
Find moles.
Mole ratio.
Yeah.
So we're going to get rid of the moles we just found of carbon dioxide and convert that into moles of, what are we looking for?
Lithium hydroxide.
Lithium hydroxide. Good. And what value do we put there?
2 and 1.
2 and 1. And this is a pretty critical step that if you don't balance the equation correctly and say, oh yeah, it's balanced as written, then you will kill your crew halfway through the mission because you're going to need twice as much.
Are we done?
Are we done? Yeah.
Yeah, I believe so.
So if we stop right there, we'd have what? Moles of lithium, right? So no, Timmy, we're not done yet. We need to convert the moles of lithium to what? Grams. Very good. What's that? No, we were given grams, and then we needed to change it to moles. So here's the beauty.
Why did we go from grams to moles back to grams? Why didn't we
Okay, yeah, good question. So here we go. Here you have moles of carbon dioxide. Here we have moles of lithium hydroxide. So the beauty of stoichiometry is you have 2 different things going on. So we want to make sure that we start with what we know, convert that to moles so we can cancel it out. Because again, this is gone, right? Moles of carbon dioxide are gone.
Right.
Now we have moles of lithium hydroxide. So we got to find out how many grams that is.
Okay.
It's 23.948.
Well, hold on there, cowboy. Let's get the mass here.
Alright.
What's molar mass of lithium hydroxide?
23.948.
23?
0.948.
23.948? I kept hearing per over there.
4.
4, my bad. Okay, so now that would give us grams of lithium hydroxide, which is
19589. That's wrong.
1,000?
19589.3
Hold on there.
Yeah.
Let's see
I
what
got
we got.
2 times 10 to the fourth.
Now that's what I gave.
That's 18 times 1,000 times.
It's 1,000,
985.
589.
What? 589.
Great. Okay.
Yeah.
Wait, why did
I
you go
said.
so
I
answer?
It was rounded.
I said it like 10
It's
times.
a benchmark. You wouldn't write 2.0 times 10 to the whatever I had on
I
your
said
board.
like 10 times.
You weren't saying the right
Yeah,
number.
I said 1 times 5, 8, 9, 23.
All right. Wasn't that a fun one? That's like a real life type problem where we got astronauts and lives at stake. I know.
Could you imagine if you would have killed those fake astronauts?
I feel bad. That would be bad.
Yeah, me too.
Keep the fake astronauts alive. Hey, we got one more.
Yeah.
Try this one on your own and don't peek up here. Try that one on your own. No peeking. Don't peek. No matter how tempted you get, Timmy, don't peek. Don't peek. Another combustion reaction. Man.
So what is it?
No, don't peek. Come on, Tim.
I'm not peeking.
Don't peek. Don't do it. No matter how tempted you get, don't do it.
What's a hydrocarbon?
I don't know. Kilograms? What a great question. Oh my gosh. This is why you got out of bed this morning, right here.
It is.
Nah.
Is that balanced?
Oh, yeah. Should balance that. Is that balanced?
No.
What would you do, Timmy? Would you put a 3 there?
Yeah.
And would you put a 4 there? And would you put a 5 there?
No.
Okay.
No, why?
No?
No.
No?
3, 3. Yeah, 3, 3.
3,
No,
3?
That's
Yeah.
wrong. It's 5, 3.
No,
Okay.
It's 5 before.
Good job there, Timmy. Nice. And
oh yeah.
it's all right, Timmy. I got you.
Hang on.
What's the matter?
Why are we going smalls?
Oh boy. Oh boy. That's a problem.
Keep moving.
No, there's no peeking.
What? Yeah, you want price. No, it's in line. It's all right. First of all, why did we go to Grams?
Why what?
Why did we go to Grams?
Why do we go to
I
Graham?
get it. I get it.
I did.
Oh wait,
Greg.
I forgot to do one more step.
You gotta
Sorry.
put it in kilograms.
Yeah, my bad.
Mr.
I
Craig,
did the work in my head.
stop doing the work.
Sloppy.
My bad, my bad. Here we go.
You got that sloppy way.
Why do people stop watching the video after this? They're so confused.
They won't. There's no way they would stop watching the video
Yeah, I will.
until it stops.
I can't imagine why anyone would stop watching one of these.
Thank you.